Invite the topic by Gosia.
So, hi everyone, my name is Malgorzata Chmiel, or Gosia, that's the shorter version of my name, and I can explain why this works like this if you're interested. But what I will talk about today is how can seismology provide a better understanding of Alpine hazard and hazards such as, for example, break-off events, so basically failure events from unstable glaciers as the one that you can see here. And I will show you some examples in which actually looking at the microseismicity on glacier works, and also in which machine learning works as well. Yeah, I can then discuss a little bit the limitations of the methods, but yeah, anyway, let's move to some hazardous mass movements. So here you can see an example of different type of mass movements in Alpine catchments. So mass movements is a geomorphic process that describes the transport of material driven through gravity. And this kind of process it can occur in different forms as floats, slides, and falls. And as you can see, these processes can be very rapid. They can transport large quantities of material in a very short time. And so basically, they are an important form of erosion, and so they shape the landscape. So that is why it's important to study this kind of processes on the quite general level. And moreover, due to this suddenness of the processes and their rapid aspect, they have a destructive potential to people and infrastructure, what we saw today. And moreover, this risk is also intensified under ongoing climate change. So at the same time, this kind of processes, they also act as seismic sources, since when material impacts the Earth surface, it generates seismic ground shaking, and we can record the seismic ground shaking with seismometers. And as you can see here, you have an example of seismic signature of those different processes. And the seismic signature looks different depending on the type of the process. We have different amplitudes, we have different duration. And it has been shown since some time that we can use this kind of seismic signature and seismic data to analyze the dynamics of those events, flow rheology. Since the seismic data is also continuous in time, we can, as Eric mentioned, we can look into the meteorological information, so try to identify triggers of those events, look for precursors. And finally, we can also use the seismic signature in warning systems, similar to as we do for earthquakes. And these are just some references. This is non-exhaustive list, but just to show you that there is already some body of research, of course, centered around this topic. But despite all that, we still have some challenges. And here are some of the challenges that I think are quite important. For example, to try to understand better mechanism of initiation of this kind of processes. Moreover, try to quantify the dynamics of extreme surface processes that can be associated with extreme weather events. And then also the question is the applicability of theoretical models, especially to this kind of extreme surface events such as catastrophic landslides and floods, how well they can represent the complex real life processes. And also we often have sparse observations in time and in space. And finally, another challenge is reliable and autonomous detection for warning. So we can, of course, discuss those challenges after my talk or a bit later. But what I will show you today is two case studies that will address the challenge of trying to better understand the processes leading to those events, the processes behind the initiation, and then also how what kind of methods we could use for reliable and autonomous detection to try to go towards warning systems. Good. So the first thing I will talk about are seismic constraints on damage growth within an unstable hanging glacier. And then I will show you how we can use machine learning combined with seismic data to go towards debris flow warning. So let's first start with the Eiger Hanging Glacier that is located in the Swiss Alps. Here, the Eiger Hanging Glacier is located on the Eiger Mountain. You can see the overview of the glacier location here. And so it was a hanging glacier. So basically, it's a glacier that is suspended on the mountain face. And for the Eiger Hanging Glacier, its spatial extension is limited with this topographic discontinuity that you can see here. And basically, those break-off events occur from the front of the glacier here. And the break-off events are just failure events, ice failure events. And they are driven by gravity. Whenever the ice is transported over this discontinuity. This is associated with the end glacial damage growth, and then a break-off event occurs. And so for the Eiger Hanging Glacier, we have those periodic break-off events that have a volume lower than 10,000 cubic meters. And if you ever been to Jungfraujoch, maybe you've seen this glacier. Jungfraujoch is one of the top tourist attractions in Switzerland. So basically, this whole area is very touristic. There is also a train station that is located just below the glacier. So that is why it's quite important to monitor those break-off events and also monitor the glacier. So what happened in spring of 2016, there was a large crevasse. So crevasse is a failure within the glacier that was observed behind the glacier front, which suggested that there is an impending break-off event coming up. So that's why the glacier was quite heavily monitored, starting from spring in 2016 until August 25. So this is when the break-off event occurred. So the glacier was monitored with an infrasound array that was located below the glacier, interferometric radar that was measuring the velocity of the glacier front. We also had 4 3-component seismometers that were installed directly at the glacier, and there was also an automatic camera that was photographing the unstable ice mass. So for the break-off event that occurred had a volume of 50,000 cubic meters. That was the largest break-off event since the 90s. And for the impressions, you can have a look at this picture here. So this is basically the mass that detached from the front of the glacier. Yeah. And now, so as I mentioned before, we had this interferometric radar measurements. And it has been shown that good forecasting predictions can be achieved by following the maximum front velocity of this unstable mass that shows power law acceleration just before the break-off event. So this is how this event was forecasted. However, what we also heard today from Eric, this kind of measurements focusing on the glacier surface, they do not show us the full picture because the failure event is associated with damage growth within the ice. Also, there might be glacier hydrology, basal conditions of the glaciers that play a role into the development on the preparation of the failure. And that was basically our motivation here, to try to use seismology to get some more information into the damage process that precedes this failure, this break-off event. So once again, here you can see the location of the 4 stations that were installed on the glacier. They were quite close to the glacier front. And also what we heard today, this kind of on-ice installations are quite challenging. Here we are at the altitudes of higher than 3,000 meters above the sea level. So due to this kind of challenging context of seismic acquisition, only one station was working continuously for 4 months and a half. And this is the impression of the seismic installation. The station was installed within the ferns of the first layer of the glacier. So one thing that we can look at, what was also mentioned today, to try to understand better the damage propagation within the glacier ice, is just by looking at this microseismic activity on the glacier, so icequake activity. Icequakes, these are co-seismic brittle events that can be associated, for example, with tensile fracture opening or tensile crack opening. And it has been shown by one of the previous studies that just by looking at the temporal evolution of this microseismicity on another unstable glacier, it actually showed a similar power law acceleration as the velocity of the glacier front. However, it occurred before, since we had this information at the depth. So that's what we did here. We'll first look into the icequake activity. And this is marked here in black. So we have the icequake activity roughly 2 weeks before the breakoff event. We have lots of icequakes. And what you can see here, that the icequake activity increases, but only a few hours before the breakoff event. So this is a few days after this power law acceleration was observed. So basically, it means that here, just by counting the number of icequakes, we cannot really get more solid insights into the damage development. And also, this icequake activity on the Eiger Hanging Glacier is not sufficient to forecast the breakoff event. But we can get some additional information by looking into the waveforms of those icequake events. So what we did here, without going too much into technical details, we basically looked into multiple icequakes. So those icequakes, these are those close-spaced events that have nearly identical source mechanisms. So it means that they have similar waveforms, and we can look for them with cross-correlation-based approaches. So this is what we did here. We divide icequake seismograms into 30 clusters of multiple icequakes. You can see the spaghetti plots of different clusters here. This is not very well visible, I know, so just have a look at one of the clusters recorded on the north component of this one station that was working over 4 months and a half. So here we have the temporal evolution within the icequake cluster. We have time within the waveform. And there are already a few things that we can spot. So first of all, we have the direct arrivals. And then you can see these arrivals that arrive later. And as we heard today, these are the coda waves. So we can observe this strong icequake coda. And this is quite interesting because for those of you who have been working with glacier data, usually when we work with glacier data, we have those different icequakes. But for glaciers, like Alpine glaciers that are quite homogeneous, we see this minimal icequake coda. However, for hanging glaciers, since they are heavily crevassed, this kind of pervasive damage within the ice generates this pronounced coda that we can observe on this figure here. And also, there is another thing that is quite interesting here, that we can see those variations or changes within the coda here, that there is, we can clearly see it just with our eyes. And so the question is, what kind of process generates this kind of variation within this strong icequake coda? And this has been also mentioned quickly today, that we have different type of perturbation that can impact or change the coda waveforms, and they leave a different imprint on the coda waveform. So we can have source location perturbation, scatter location perturbation, and velocity perturbation. And we can measure them by using coda wave interferometry without going into too many details. And now, yet another question is, which kind of perturbation is the most prevalent for the Eiger Hanging Glacier? So here, we make an assumption that most of the scattering on the Eiger Hanging Glacier occurs on big crevasses, so big fractures, that takes longer time to develop than 4 months and a half, which is actually our study period. And then we can look into source location perturbation within the cluster and velocity perturbation independently. And I'm not going to show you the velocity perturbation results since they were less interesting. Basically, what we saw is just seasonal decrease in dV, or the decrease in dV over V that was associated with the seasonal increase in the glacier ice and firn pack temperature. But I think what is quite interesting here is this kind of source displacement that we can measure with Koda wave interferometry within each cluster. So here we have 2 months of data. That's the source displacement that we measure, and each color shows different cluster. And one thing that we can also, so this is the break-off event. And yet another interesting thing is that there is one cluster that stands out from the rest. So I will talk about it a bit more in the next slides. But of course, another question that we can ask, like, what is the source mechanism of those clusters? Which processes generate those ice quakes? And without going too much into detail, I can talk about it a bit during the discussion if you are interested. But basically, by analyzing the daily activity of multiple ice quakes, and also by looking into cumulative displacement over those 2 months and comparing it to glacier bulk displacement, and also by having an approximative information about the location of those clusters, we proposed that most of those clusters are extension events of crevasse tips. So basically, they can be most probably cracking events within the ice that contributes towards crevasse extension, so towards the fracture extensions within the glacier ice. And with that, let's go back to this plot here for one of this cluster that once again stands out from the other cluster. So here it's marked the displacement, the measured displacement for 2 months. It's marked here in purple. Other clusters are marked in gray. Here we have the break-off events, and here, for comparison, we have the measured maximum velocity of the glacier front. So this is the velocity of the unstable ice mass before the break-off event. And so for this cluster, it's quite interesting that it appears roughly 30 days before the break-off event, and also its activity stops just after the break-off event. And another thing that is quite interesting here, that actually the velocity of the glacier front, so of the unstable mass, accelerates in parallel also with this measured displacement with Koda wave interferometry. So now, to kind of quantify this agreement between our observation, which is source displacement, and the velocity of the glacier front, we used the damage mechanics theory for ice rheology, following previous work of Antoine Pralong, that allows us to link the velocity of the glacier front with a damage variable. And for the damage variable, to parameterize this damage variable, D, we use this displacement of the source, because this parameterization assumes that this maximum displacement, the damage that describes the integrity of the ice, can be associated with this fraction of the ice that combines the unstable part with the stable part of the glacier. And basically, when this ice bridge is fully damaged, this is when the break-off event occurs. So we use that, and then we have this physical model. And once again, we use the displacement as a damage parameterization. And this model shows the 90% agreement with the measured front velocity. So this is the modeled front velocity of the glacier by using, once again, our observation. So this is actually quite interesting. Of course, this is the case where it worked out pretty well. This kind of method, to my knowledge, hasn't been, of course, this method has been used in other settings, but not on unstable glaciers. And I think it hints us that we can, with seismic interferometry, we have this potential to measure directly and glacial damage. And this, of course, could be also used on different glaciers, explore existing data, also on ice shelves, maybe on unstable slopes. And I think also another thing that is quite interesting here is that this acceleration of the source displacement appears before we can see this power acceleration at the surface. So this actually could be an argument that, or it is an argument that if we look into depth processes, we might be able to gain some insight into this processes or damage processes occurring at the interior of the material before they manifest at the surface. So this is the first part. That was a little bit more technical. The second part will be a bit less heavy on the methodology, but yeah, I don't know if you have questions here, or I can go to the second part. Mm-hmm.
Thanks for the question. How do you compute the displacement from the seismic?
Yeah, so I didn't go into details here, but basically we use Koda wave interferometry. So we can measure not only the phase shift, as Eric was showing, but basically the correlation of the Koda waveforms between reference function and before reference waveform and before a waveform at the given time. And then with that, we can calculate the source displacement. So this, the actual equation, I don't have it here, but you can check those two papers, or I can also show you and explain with the equation after the talk. Yeah, it's based on the decorrelation measurement of the Koda waveforms.
So actually, as you're already on this slide,
Yeah.
it seems like the scattering properties of the medium actually changed quite a lot. Like judging from just the amplitude of the Koda. What I was curious about, whether you had measurements after the breakout. Like I was just wondering how it would look afterwards.
Yes, that's indeed, it is a quite critical point, and I will talk about it a little bit later in terms of like those gaps or like the unaddressed rust gaps. That's a pity, because here we only had those 4 months of data, and basically the data, like the seismic stations were deinstalled like after the breakoff event. So yeah. But it's true, and actually, so here, regarding the changing of the scatterer properties, so this is also kind of a simplification, because most probably it's the source displacement and also potentially some changes in the scatterers that drives these changes in the Koda. But yeah, since the big crevasses, they develop more over the time period of more than 4 months, that's why we propose to look into source displacement here.
So you compute this source displacement for all the, what was it, 27 or 30 different clusters, right?
Exactly.
And these clusters, these are clustered based on the waveforms.
Yes, exactly. Just based on template matching.
And that these 30 different clusters are different types of events.
So there are different types of events, but they might have the same source mechanism. Or this is what that's what we assume here, that based on these other observations, that most of those clusters are associated with cracking within the ice.
Because this strong source displacement, you only see it in one of the clusters.
You mean that's the strong? You mean in terms of?
I think it's the previous slide.
Yeah. You mean the displacement that we only see it.
Source displacement. You only see it.
Yeah.
Cluster number.
Yeah, 24. Yeah. So that's actually. So this is. That's why. That's what I'm saying, that it worked out here. But that's the thing, that it's only one cluster. And of course, there is also crevassing happening at the glacier in different parts, not only at the glacier front. So potentially it could be that. But that's why it would be very interesting to use the same methods with different data set and try to understand a little bit better what we can actually obtain. Yeah. Mm-hmm.
So maybe you just answer the question. So you're assuming that the sources are all about in the same region?
No. they are not all in the same region. And here what we did, average localization, because the 4 stations were not working at the same time, but we applied match field processing. And then we basically get like 2 location spots in 2D, and 1 points towards the glacier front, and 1 points towards the back of the glacier, where there is also a crevasse where the glacier is attached to the, But that's the information that we were able to get with those data.
A question is about the cluster, the number of clusters. How do you decide to use 30, or is it only increasing to 30 27?
Yeah, so this is also simplification here just for the sake of the presentation. So basically we used RedPy and template matching, and RedPy is this kind of tool that allows you to cluster your data automatically, and you don't have to define the number of clusters. Basically it takes the data and then it just clusters on its own, and we got 550 clusters. And we just then took the 30 top ones that had the highest number, more than 100 events, or like some certain, I don't remember exactly, but certain number of events. Yeah.
So it's automatic?
It's an automatic, but then we made this selection to look in the most active clusters that had the most events. Yeah. Okay. Anna, I don't know if you had a...
was answered. That was more about if you indeed located the clusters, and if the cluster that showed like the increase in source displacement, if that was located in the unstable part.
Yeah, that points towards the front. Yeah. Mm-hmm. Yeah. Okay, and just the second thing I will talk about, but without going that much into methodological details, it's machine learning that was already discussed today. Applied to seismic data, and to try to use this kind of approach towards debris flow warning. So we are still staying in Switzerland, but we look at different type of surface processes, which are debris flows. And here you can the study site is Ilgraben. It's a very active catchment located in Switzerland. And debris flows, you can see that these are this kind of rapid mass movements that are mixtures of water, sediment of different sizes, and also very large boulders. So here you can see the front of the debris flow that approaches, and those heavy boulders that are also, these big rocks that are mobilized by the debris flow. And so here also to illustrate a little bit better a debris flow event that's a cross-section, longitudinal cross-section through the event that shows the main characteristics. And in terms of seismic signals, since due to the particle segregation within the debris flows, those heavy boulders are pushed towards the side, to the front of the flow, and this is basically the part of the debris flow, so the front, that it's more seismically loud. So when we record those debris flows, this is basically mostly what we see in the seismic data, this boulder charged front. And a few more words about Ilgraben. So Ilgraben, it's a kind of a hotspot for debris flow studies, because those kind of events, they occur regularly each year. In Ilgraben, we have more than 5 debris flows and sediment transporting floods per year. And the events are triggered usually by heavy precipitation in spring and in summer. And they result from a cascade of different processes. So basically what happens here, that in the upper catchment of Ilgraben, there is lots of rockfall and landslide activity at those steep slopes. Then those sediments accumulate in the channel, and then during heavy precipitation, sediments are mobilized and they propagate down the channel towards the Rhone River as debris flows. And what you saw also on this video I showed you, that was one of the check dams, which are like concrete structures installed within the torrents. And they were installed to kind of stabilize the channel, minimize erosion, and also reduce the runoff of those debris flows. So you can see an example of one of the check dams, the lower check dam here, and 4 different debris flow events. And at this lowest check dam here, there is a debris flow observatory for research purposes. And what we can see here also is that those debris flows, they are very regular, but also they are variable in the sense that we have different sediment concentration, different water content, and of course different velocity of propagations. And the current warning system that is used in Ilgraben to warn against those debris flows relies on in-torrent installations. So basically it means that the system needs contact with the process, with the debris flow, to make an alert. And the earliest detections are made at check dam 1 that is installed here. So basically it means that there is this upper part of the Ilgraben catchment that is not covered by the warning system, and this is a major blind spot. So that's why that was one of the motivation for our seismological work here in Ilgraben, to try to actually come up with a method that would be able to detect those debris flow events as early as possible when they initiate in the upper part of the catchment that is not accessible with in-stream measurements. So that's why here, since 2017, the group of Fabian Walter has been installing 8 seismic stations in Ilgraben. And so this study was done in 2020. And by then, we had 22 events that were recorded over 3 years. And you can see an example of one of the events here. That was one of the largest events with a volume of more than 80,000 cubic meters with a front velocity of roughly 6 meters per second. And once again, the concept of using this kind of seismic data for warning is that also we are able to reach areas that are not accessible with other type of instruments, and also seismic waves, they propagate faster than those kind of processes. And here, Fabian, with his group, they try to use amplitude source location to locate and detect debris flow events. But this kind of more traditional approach was very prone to false positives. So basically, whenever there was a strong source, like a walking cow, for example, next to the seismic station, then this algorithm was thinking that that might be a debris flow. So there was lots of false positives. So that's why we also thought, okay, maybe we could try some machine learning and see if this would help us with those false positives. And just on a very high level, basically we pose this problem as classification, which is kind of similar to speech recognition. So basically we try to classify or recognize different type of signals. So to distinguish especially between debris flow events and, for example, anthropogenic noise, that might look quite similar if we just look at the waveforms. And for that, we use supervised machine learning, and we divide the signals into 3 different classes. So we have the early debris flow class before the check dam 1. So this is the class in which we are the most interested. So basically, this is when the debris flow is forming and before it arrives at check dam 1. We had a late debris flow class when the debris flow is well formed and travels down the channel towards the Rhone River. And then we have noise class, so basically anything else that is not the debris flow. And since we only had 22 events, that's not a lot to do machine learning, but each of these events was longer than 1 hour. So what we did here, we just divide those seismograms into 100-second long time windows, and with that, we ended up with a data set that was large enough to do some machine learning. And once again, so when we use 70 features that were defined on previous studies, and basically feature is just a scalar that describes waveform properties, spectral properties, and network properties, so the way the signal varies within the network. And we use that with random forest, which is also quite I can discuss it later, but I think it's one of the simplest algorithms in terms of machine learning. Yeah, and more details are in the paper. So let's just move towards the results. So that was in 2020. And basically what we did, that we trained this kind of machine learning detector, and then we had completely new data that was coming like near real data streams in 2020. And we applied this detector in near real time. And here you can see the results. So we have hour, we have different Julian day in 2020. And once again, we have those 3 different classes. of signals, and each pixel here is an individual detection within a 100-second long time window. What we can see here, that those kind of snakes, blue-green snakes, these are the debris flow events that we were able to detect. There are some random pixels here and there, but usually they don't cluster that much in time. And then if we look on one of the events, so these are our detections, these are the waveforms at 3 stations and the spectrograms. And then for kind of to go towards like one step further and propose maybe like not only a detection approach, but a potential warning approach, we defined alarms that require subsequent number of detections to raise an alarms. And with this, we were able to eliminate those random pixels here, and we would be able, for this year, we would say that there would be, what we said, there were no false alarms. We were able to detect all of the events. That was also verified with different instruments. And as compared to gain in warning time, as compared to what is done so far at checkdam 1, we were able to gain between 20 minutes and more than 1 hour, depending on the propagation of the debris flow event. So that's, this is what we show in the paper, and which worked very well on this that year, and we were actually kind of positively surprised, but especially that we were able to detect those debris flow events in the upper part of the catchment, and I think also this work kind of generated quite a lot of interest of using this kind of approaches for debris flow warning. However, there are limitations. And I will be happy to discuss them in the next 2-3 slides. I don't know if I have time. Yeah. So one of the limitations, or one of the question is how transferable is this approach? So we trained it on data from 3 years. In 2020, it worked perfectly, almost perfectly. But then we applied it in 2021. So once again, we have the same plot with different classes, and we have way more of those individual pixels that are misclassified as debris flows. So basically, it means that most probably what happened, there was a new noise source that we didn't see during the training process, that we didn't include it in our data. The model didn't know that this is noise, this is not the debris flow, and this kind of misclassification occurred. So this is, of course, one of the ways to go forward, try to update this model, but with noise sources, because the debris flow signature doesn't change that much over a few years, but the noise sources, especially the unprogenic noise sources, might change a lot. And so this is something that Patrick Pietz is working on, to try to go towards a generic debris flow detector, try to combine different data sets from different catchments, and also use non-supervised machine learning. And this is one of these results. So maybe this is one of the way to go forward. And then one more thing, so we also try to apply the same approach based on machine learning, but to detect different type of mass movements, so rock slide events such as rock falls and debris avalanches on a large-scale rock slide in Switzerland called Spitzenstein that is very active. And here, once again, we had 3 stations, different type of process, and that's, again, that's the work in progress, but one of the main things was really the question how to represent the noise class, because the issue wasn't even the ability to detect those events, so mass movement events, but how we can reduce the number of false positives, and because here in the end, one single class for all the noise sources was not enough to accurately classify those seismic data. So I can discuss that. I'll be happy to talk about it later if you have some questions or during lunch. But just to go back to those different questions. So those are the challenges that I mentioned, and I showed you how we can address some of them with seismology. I think short-term focus, this is basically try to address those challenges here. So for example, sparse observations, of course, right now we have DAS that opens all the range of possibilities to go into more dense observation of such processes. I think in terms of precursors, what is also interesting is not only the temporal occurrence of this event, but also be able to make a statement whether a failure will occur in one piece, in multiple pieces of material, and which is also, of course, related to the risk of those processes. Maybe ideally say something about the unstable volume. So this is where we need those information at the depth. Long-term focus, and I think this is already short-term focus, but something that will probably become more and more important is climate change impact on natural hazards. To say something more, which events are impacted, in which way, and of course, because we know that climate change is impacting this kind of events. But it's not always easy to make a quantified statements. And blind spots, something that maybe a bit more subjective. I think cascading hazards. So this kind of process, they can occur in cascade, where we have, for example, a large landslide that will generate a dam that will kind of block a river. Then there will be a flood. And to try to understand this kind of cascading processes and also their impact in short scale, long scale. And finally, I think is one of the challenges and kind of a, so that I think there's also the challenges to go into interdisciplinary collaboration, because it's not only seismology, it's an interdisciplinary topic. And also the blind spots data continuity and accessibility, because those kind of processes in Alpine catchments that are studied also by private companies and so on. And those data is sometimes not shared. And finally, also what was mentioned here, that to have data continuity, to look into those kind of processes over a longer time, not only at the scale of a few months or one season, but to have also this inter-season, inter-year variations. Okay, thank you.